Hello, this is going to be Sun Part 2. Just did this in my classes today. If you remember, the first rule is never look directly at the sun unless you've got your money's worth of eye gear. Just a quick way to impress that once again. If you're actually looking through a pair of sunglasses, not expensive enough. If you're looking through a telescope, hopefully you paid a lot of money to get a sunscreen that blocks out 99% of the solar radiation. Today what we're going to be talking about is more like the interior of the sun, sort of what this picture has been showing you since we started. Got to get back down to a right size. We're going to start talking about the core. We're going to work ourselves out around the radiative zone, through the convective zone, through the photosphere, through the chromosphere, and then right into the corona. Okay, so once again, Soho provided most of the images that I've got in this presentation. You can look up Solar Heliospheric Observatory or just Google Soho and see lots of images. SWABAT students will be able to. These are the three things I hope you get from this presentation. What are some of the characteristics of the interior of the sun? What processes occur in the interior of the sun? And what are the major surface and atmospheric features of the sun? The first picture I actually showed them today was this picture, and I got this off of a site a few years ago. It actually shows the sun as it moves down from the southern sky, arcs down in towards the western sky, and if this is the equinox, like it is sort of around here, not a very good W, it's going to set directly to the west. If it's a little earlier in the season, winter-wise, it's probably a little bit south of west. If it's a little bit later, summer-wise, it's going to primarily move a little bit north of west. But right now it's moving through. And what I wanted them to see was the color change in the sun as it gets a little bit more red. And the way I explained it, I gave that as the Earth. I gave this as our atmosphere. And then I drew the sun like up here, and I imagined them as standing on this planet. Got to give them a waist. And as they look up, what they're going to notice is they're looking through this much atmosphere toward that sun. And what happens is the three primary colors of blue, yellow, and red. The blue gets scattered first with our chemical composition, and this is why we have a blue sky. If you move to Mars, they've got a reddish colored sky. If we could actually get rid of the gases and replace them with things that could actually do the blue and the red, we would have a purple sky, or blue and yellow. We could have a green sky, or yellow and red. We could have an orange sky. We are stuck with the blue. Blue is a beautiful color for the sky. But if we're looking through here, blue is the first color that actually gets diffracted and reflected in our atmosphere, which is why we have a blue sky. As the sun gets lower and lower in the sky, we look through more and more atmosphere. And I tried to actually tell them, I said, if this is atmosphere 1, what is this one? This is maybe 1.2. And what happens is the blue light gets scattered a little bit more. Then as the sun sets lower in the sky, we're looking through more atmosphere to see it. And eventually what happens is the blue light disappears. And then what do we have? We have an orangish colored sky. And you've all seen clouds out there. I don't think I really have, maybe orange. You've all seen clouds out there as the sun gets lower in the sky, have this orangish type of color to them. And then as it gets lower and lower in the sky, this of course gets more and more red as the yellow disappears, and then the red disappears, and usually by that time the sun has set. So if we actually had a sun way over here, we are looking through a lot of atmosphere. To see that, if we come over, looks like about that much. And what happens is the blue gets dissipated in this area. Let me actually do blue. Blue gets dissipated in this area, so if you were standing right about here, you'd expect to see a blue sky because you're only looking through this much atmosphere. But the next color that disappears is the yellow, because the yellow shows up for a while. And this actually allows us to get rid of the blue, and the yellow and the red is going to be there. And then pretty soon the yellow disappears and all we get is red. So this is why the sun and the sky actually has these different appearances. Okay, if I erase this thing, at least some of it, let me get a bigger eraser. Okay, if we actually get rid of at least some of this diagram, we can talk about this one. This is actually a picture of the sun. It talks about the location of the hydrogen fusion, where we actually get hydrogen ions, and we give them enough speed that we can actually see these things. And can I pause this puppy? Okay, and as I was saying, we can actually have this hydrogen ion plus hydrogen ion, and we can actually get them going hot enough and get them hot enough so they can move fast enough so they can finally escape. I want to show you that right here. This is a site that we can actually add more and more hydrogen into a system, and as you can see, we just had 2 hydrogens actually fuse. There's a third one. Have another one go right there, and we keep adding more and more hydrogen, more and more fuel, we can get more and more fusion. And if you don't like that, you can actually increase the temperature. And as the temperature goes up, we get more and more fusion. And just like the sun, when we actually run out of hydrogen, or the hydrogen gets to a point where it's so far away, and as you take a look at this, you can see more and more black, less and less of the reddish color, the hydrogen, because they actually go into that 3-molecule helium molecule, and there's the couple of 4s too. And you can see those in there. So we've got these things actually popping in and out, less and less of the actual fusion reaction because our fuel is dissipating. What we'd like the sun to be able to do is to add more and more hydrogen, which you can do on this simulation. Unfortunately, the sun can't go to a service station and say, more hydrogen, please. Okay, so this is where the hydrogen fusion actually occurs in the core. It's also because it's made of an incredibly hot 15 million, that's cool. I don't know what's going on here. Million degrees, or million K. 10 million degrees is what we need to get hydrogen ions to move fast enough to fuse. We have about 50% more heat than that. That heat gets transferred out through a form of energy transfer called radiation, where it moves directly out away from the core, and then it actually moves to this convective zone, which is out here, which you can see the convection cells, where things rise because they're hot and they sink because they're cool, and they rise because they're hot and they sink because they're cool. Percent of the sun, which is on here, which we'll talk about later when we actually get to another stage in this presentation. I had my kids draw this picture. I had them actually take a circle, probably 2 to 3 inches on their paper, something like this, going around a little faster than I went around in class. Then draw a line that goes down here. If they really wanted to make a 3D version, they could actually arc it. Draw the core there. This is where we actually wrote core inside. We also wrote 15.6 million degrees around here. I had them draw some lines that go out from the core. I said 4 or 5 lines out from the core, showing you the radiative zone and the heat transfer. Here's where I actually added the numbers. We called this 0% away from the center. This goes out to 25% of the center. This one goes out to about 85% of the center. Then we drew another line up there right underneath it for the photosphere, which we said was around 99% from the center, and then the surface, the top of the photosphere, which would have been 100% all the way out to the surface. Also had them draw sunspots with that gray area around it, which we called the umbra and the penumbra, just like we do for an eclipse. We talked about the faculae, these lighter areas. I actually told them to do it in white. They're luminous clouds. right over the top of the photosphere with sunspots are on the surface, which is the photosphere. We'll talk about those down here too. Also talked about this picture, which I really like, and let me pick a color we can maybe see. And this is the way the random photons, the light and the heat, works through the sun. And you know, a lot of times people think this thing is moving at the speed of light. It doesn't. It moves at a much slower rate. On average, it takes 23,000 years for this light to make it from the center of the core, where it's actually being produced, all the way out to the surface, and then 8 minutes and 20 seconds to make it all the way to the sun. So it does take a phenomenal amount of time. Here's where I was actually talking about this site. This is the site. If you actually type in this much into Google, and then you type in fusion, there are lots of cool sites from here, Lives of Stars, which I'll talk about when we do the next presentation, as well as lots of other things. Okay, I also had him draw something that looks like this, which is the way I've always drawn a prominence, drawing some lines there, and then lines in there. Give you some idea of the prominence and the fact that it actually goes out here all the way out to the corona. Prominence comes off the lower atmosphere, which is called the chromosphere. The chromosphere they're actually saying is this line. I had them draw spicules. I told them they look like this, small little jets of gas that are coming up all over the sun. I want to pause it here. Okay, then I had them actually draw some dots in here to actually represent the granulation that's showing up here. It's actually sort of like the spicules actually showing up. And I think I can probably show you the granation. This is granulation. These are the actual spicules. And if you take a look, we have a bubbling cauldron of material, where material's bubbling up out of the sun, and you can also see it moving back into the sun. It's more like a convective thing, but it gives the sun a very granulated surface. We didn't know exactly what it was before we came up with the terminology, but this is the way we can actually look at this granulation. Okay, then we talked about prominences we have there. This is a closed prominence. They're actually showing you some other things here, which may look more like open prominence. And I had them draw lines sort of looking like this for open prominence. I think that's all I had them draw, but I may have to come back here in a second. Then we talked about solar innards, characterized by two things: the temperature differences and the density differences. So if we go from the core to the radiative zone, we actually change density and temperature. Go from radiative convection, temperature, and density change. So we actually do have this layering of the sun, just like we had layering of the earth. We talked about the core being hot, dense, central region, actually with a nuclear fusion, that hydrogen fusion that's going on, that powers the sun, and we said it comprised 25% of the interior. It went from 0 to 25%. The radiative zone, comprised of that part of the sun, 25 to 85% of the solar radius. It's called radiative zone because the heat transfers through radiation, and all I wanted to know is that it takes the heat produced in the core and transfers it out to farther outer layers. The convective zone, 85%, and I had them actually right here to maybe 99%, and this will actually cover a small portion, but it is a convective way, and I had them draw arrows to actually show the hot stuff rising up to the surface, passing on its energy to the last layer, and then cooling off and dropping back down to be reheated, and we drew 5 or 6 of those convective cells inside there. Then we got to the photosphere, and that's the actual 99 to 100%. Photosphere is the actual surface of the sun. Bring it down to here. All I wanted to know is that it's the area that produces visible light. It's the surface you can see with your eyes. It is the location of sunspots. I showed you this granulation video. This is what the sunspot video looks like. Take a look at the granulation on the outside. You can also see the very darker part, which is called the umbra, and the lighter part called the penumbra, and you can sort of see those if I show you both of these. The umbra is this inside part right there, and the penumbra is this other part, and I had them draw this on their notes as well. And the way I had them draw this was to take a black area and make a thing like this, and then go ahead and darken that whole section in, and then with a thinner pen draw some lines that goes around this area and gives the idea of this two-layered thing. And then we wrote the umbra and the penumbra to actually list that. And we have the same thing. We've got the umbra and the penumbra, and this was just to show you the size of the Earth compared to sunspots, and sunspots can be large. Then they did a web assignment, which actually I may be able to put this thing up later too, but they were studying sunspots. They figured out a sunspot is cooler because it is, instead of 6,000 degrees, and let me go back up to this picture, because we did add this. We said this was 15 million. Okay, we said out here the photosphere is 6,000 K, and then the sunspots, when we finally got down here, why are the sunspots cooler? I said if you could actually bring a cupful of this into the classroom, it would be the brightest thing they ever saw right before they got incinerated. But we did talk about the fact that the sunspots were cooler, somewhere between, I can't do that with black, somewhere between 4,500 to 5,000 K. So it is darker because it's not quite as hot, although it would be bright in most circumstances. It's not bright when you compare it to the 6,000 degree surface of the sun. Okay, sunspot numbers. If you take a look at this chart, we actually have 90 degrees north, 30 degrees north, the equator, 30 south, 90 south. We have 1870 all the way up to 19, probably 05 or 06. And what they were trying to show you, what I was trying to show them, is that this is like a map of the sun on a flat piece of land, a two-dimensional flat sun. And the way the sunspots actually work, I'm going to start with like 1878 here. The very first sunspots seem to appear, and probably not the right color, seem to appear in latitudes that are less than 30 in both hemispheres. And as we get further into the cycle, and I asked them if they could actually see cycles here, and it's actually, I think, pretty easy to see. I did talk about this one right here, where we actually had more than 200 sunspots occurring in 1957, the year I was born. If you take a look, it looks like we actually have an increase in the number up to this point, and then it seems to decrease down. And maybe if we actually continue this to 2050 or 2060, we might find out that it spikes up there, but hopefully not as high as on my birth year. But anyway, these sunspots get up a little higher, they go down a little lower, and then they just keep changing with the time. So as they start appearing, a little less than 30 degrees, then they get a little higher. This is what's called the sunspot butterfly. And I also did show them that right along the equator, we don't get very many sunspots. We also don't get very many sunspots by the poles, but you can see some of these get fairly close, but not very many. Most of them actually happen between about 35 north and 35 or 40 south, but they actually start appearing here, and then as time goes, they get closer and closer to the equator, and then they just kind of like disappear. So this is the minimum. and then we get to this point right in here where we have large areas in both hemispheres. That's the maximum part of the cycle, and the cycle actually happens around every 11 years or so. Okay, above the photosphere we have the chromosphere, and the chromosphere was, sorry if I go too fast for you there, chromosphere is this roundish area. It's the lowest level of the solar atmosphere, and it adds a little bit of hydrogen light spectral to it, adds a little pinkish color. Chromosphere actually means colored sphere, and that's because we get some hydrogen, and if you ever get a chance to look at the hydrogen spectra, it's a kind of a pinkish color, so it adds a little pinkish color to the yellowish white color of the sun. It's made of four things: the vacuoles, faculae, spicules, prominence, solar flares. These are those white luminous clouds in the lower atmosphere. Spicules are those small jets, and I was telling the kids they're small because they're only about 1,000 miles tall. And they can only be called qualitative rather than a quantitative when we talk about small. They're only small when we compare them to the prominence, the very large jets, and these things can be hundreds of thousands of miles tall. Okay, they can also be open or closed. Show those up there. Last thing is the solar flare, and I didn't really show solar flares, but if you take a look at this picture, they're associated with sunspots, but they're actually these large openings in the sun. And it's almost like the sun breaks open. And I made a statement that most of the kids, I think, could see. I made chili last night because we had chili and cheese dogs for dinner, and I forgot to turn off the simmer on it while we were eating, and when I went back to get my second hot dog, chili dog, I noticed that the chili had a crust on the top. And then I asked them, I just stirred it into the chili, but I asked them what would happen if I turned up the heat a little bit more and we got the chili underneath the bubble, and they said it would actually start breaking the crust, which is exactly what I wanted them to see. And it's sort of like the sun has a crust, and the crust breaks open and this stuff just comes spewing out. And I'm using the wrong color, and I don't know why I always get the wrong color. But it's sort of like this thing opens up, and these things, and that's probably get even a darker color than that. It's like the sun opens up and the stuff just comes spewing out. It's incredibly bright. It's also incredibly hot. But all four of these produce solar wind. And if you look at my version 3, which I already have posted, the Sun 3, it talks about solar wind moving out, hitting our magnetosphere, and actually hitting our atmosphere, causing the aurora borealis in the northern hemisphere, the northern light, and the aurora australis, the southern light in the southern hemisphere. But solar wind is just a plus charge, and it comes streaming out of all four of these, streaming out as many directions as the sun will allow. And what allows it? The last layer, which is called the corona. This is the outermost layer. This is where the prominence appeared, and I showed you that up in that diagram up there. It's the outer region of the corona. It stretches far out into space. This is the corona. I know when I usually draw a sun, I draw a sun with lines that look like this, and I know some people draw them with lines that look like this, and some people just draw them with lines. But what we do is we're sort of drawing that corona. Corona in Spanish means crown. This is the crown layer. But it basically moves out into space. So it leaves the sun, but just keeps moving out into space. The corona can only be seen during a total solar eclipse, which is we're having right here. Remember I told you about 400. The moon, 400 times smaller than the sun, but 400 times closer. Sun, 400 times larger, 400 times farther away. And because of that, we actually have the same apparent size in our sky, so that the moon can cover up the sun. And when it covers up the brighter part of the sun, we can actually see the corona. Another way we can actually see this, here are the two sites for that movie. Here's the Grenation movie that I showed you. And I just can download this. Here's the Sunspot movie that I showed you. Here's the fusion site that I showed you. And this is the other site I want to show you. And if you take a look at this, this is from Soho. This is the actual picture of the sun, or the size of the sun. And they're putting a disk in front of the sun. They're actually covering up more than just the photosphere, but this allows us to see the corona, and you can see that it's actually moving in all directions. This is what's called a coronal mass ejection. You can see this one actually happened January 28th, 2011, so it did happen more than a year ago. You can see how long it takes it to go out. It's about a 2+ hour video. This stuff just goes streaming out into space. If the Earth was out here, we're probably going to be in for a lot of aurora activity, as well as some other things that I talk about in number 3. Okay, I think that's all I need to do. I appreciate you stopping by. Take care.